Okay, preceding class we had this set of sample observations where we had 8 large drops, 12 medium, 14 small, and the average diameter of the large drops was 3.5 millimeters. The average diameter of the medium drops was 1.8 millimeters. The average drops of the average size of the small drop was 0.6 millimeters. And we used a formula for the volume of the drop. The formula was, and it's not written up there anymore, but I don't think this formula is actually the best thing that we could use, but I think we used d cubed over 12 for the volume. So here we evaluated d cubed over 12 for each volume, or for each drop size. So we find that 3.5 millimeter drops have a volume of about 3 cubic millimeters. Now, people who actually did the calculation for 3.5 millimeters, the actual number is closer to 3.5 millimeters cubed, and is in fact closer to 4 millimeters than to 3. But whether we use 3, 3.5, or 4, we still have the idea. And there are reasons we would actually round down to 3 because of the way cube diameters, it's the nonlinearity of the cube diameters, and you don't need to know what that means. Okay. These 1.8 millimeter gives you about 0.5 millimeter cubed. 0.6 millimeter gives you about 0.02 millimeter cubed. Then we calculated, what the volume would be if we had 8 of these, 12 of these, and 14 of these. And that's very straightforward. We just add 8 times 3 cubic millimeters because we had 8 of those, and 12 times 1/2 cubic millimeter because we had 12 of those, and 14 times the 0.02 millimeters cubed. And we got 24 and 6 and 0.28 millimeters cubed, and that rounds off to 30 millimeters cubed. Now we comment that these are just estimates. We're certainly not totally accurate with this. So these small, the 0.28 millimeter cube that we get for the 14 small drops is really insignificant compared to our likely uncertainty in estimating these things. And also in grouping these things, because if this is the average diameter, it's not the average cubed diameter. Again, you don't necessarily need to know what that means, but we're going to say this is insignificant due to uncertainties in estimates. If we're off by even 1/10 of a millimeter in this estimate, we're going to be off by a lot more than 0.28 cubic millimeters. And of course, we're using a very approximate 3 cubic millimeters, which is already off by 1/2 a cubic millimeter just based on this. And this 0.02 and all those 0.02s aren't going to make much difference. You could even argue that the 6 millimeters cubed that we get from the 12 mediums is not all that significant, but we're going to include that. Okay. And I'll say also, due to the fact that the cube of the mean is not the mean of the cubes. And if you have the mathematical background to understand that statement, it's worth pondering. Okay, not everybody does, and not everybody will have the time or take the time to do that, but I wanted to mention it. Okay. Okay, well, more accurately, if you actually do these calculations and don't round things off, it's closer to 35 cubic millimeters, but still, we don't have a whole lot of faith in that being 100% accurate. Maybe we're plus or minus 25% if we made good estimates. Okay, so and I again repeat that the 0.028 cubic millimeters is negligible given the uncertainties in our data. Okay. Now we have this stuff that's kind of a refugee from differential equations. We don't need that. We don't even want to think about it. What I asked everybody to do then was to estimate the diameter of each of the largest 1/3 of the drops. And this was, I said it, I didn't write it, this is in the third rectangle because we have now a figure where I've got a strip of rectangles marked in red, and we're estimating the numbers in these rectangles. Okay? So, that's the next task. Let's see what we get.